Let's try this more involved synthesis. We're given alpha-ketoglutarate and acetaldehyde to develop a synthetic sequence to form this compound here. So the first step is to number all of these carbons and try to see where the reactants fit into the final product. So alpha-ketoglutarate is a 5-carbon molecule coming straight from the citric acid cycle. At carbon 2, which is the alpha carbon, we have a ketone. 3 and 4 do not bear any other functional groups, and at carbon 5 we have another carboxylic acid group. Acetaldehyde has 2 carbons, and if we take a look at our structure here and count up all the carbons, we have 9 carbons here. So 5 plus 2 is 7, so it would make sense that we need to use acetaldehyde twice somewhere, or do 2 iterations involving an acetaldehyde derivative. Another thing to notice is the ketone has survived the entire synthetic sequence. At carbon 2 we have a ketone, the alpha-keto group, and we also see that here. So let's call this 2-alpha as well. Now in alpha-Kg we have a carboxylic acid group at carbons 1 and 5, and in our final product at carbons 1 and 5 we have alcohol groups. So these alcohol groups are derivatives from these carboxylic acid groups, based on our numbering scheme. So the only carbons we haven't really accounted for are these 2 and these 2 that are flanking this entire molecule. And it just so happens that these are ethyl groups. So for sure 2 iterations using acetaldehyde is required to form this alpha-Kg derivative. Now the question is, how do we do that? It seems like these ethyl groups are directly attached to a former carbonyl carbon, as we see here. So some sort of nucleophilic attack must occur. So immediately we think of Gilman or Grignard reagents. Now how do we differentiate between the two? Well, it turns out Gilman reagents are weaker, and Grignard reagents are far more reactive and stronger as bases. Another clue is that this entire compound is straight chain. We don't have any alkyl branching. And usually a pattern that we see with Grignards, especially when we deal with acyl compounds and carbonyls, is this branching pattern right here. So if we saw this compound, very likely it would be a Grignard attack on rather an acyl chloride or bromide. But we don't see any sort of alkyl branching in the final product. So the Gilman reagent would work just fine. It functions as a nucleophile and only adds one part of the Gilman reagent, so only one attack. The final clue is that at 2-alpha we have a ketone, and in alpha-ketoglutarate at 2-alpha we also have a keto group. So this ketone has survived the entire sequence, which means it would make sense to protect it and then deprotect at the very end. This is just to ensure it doesn't react with any of our strong reducing agents that may or may not be used, or the Gilman reagent. So let's start off by protecting alpha-Kg. So our starting material can be abbreviated like so. And importantly, at the alpha carbon, we have a ketone, which we are trying to protect. So to do that, we react it with ethylene glycol and some acid. Now the reason why we need acid is because this protecting group is an acetal. And we know acetals require an acid catalyst. So at the alpha carbon here, instead of the ketone, now we have our protecting group. Looks kind of like an alien. So now the question is, what do we do with this protected compound such that we improve the electrophilicity or reactivity of our carbonyl system? Well, here we have carboxylic acid groups where the OH is the leaving group. Well, what we can do is convert it into an acyl chloride, replacing these OHs with chlorines. That gives us a good leaving group and makes the compound even more susceptible to nucleophilic attack. Another way is to use the aldehyde, but let's stick with our acyl chloride, just for simplicity. So our modified alpha-Kg, let's call it compound 1, and what we do with it is convert it into an acyl chloride. And to carry out this conversion, we need thionyl chloride. The common solvent with thionyl chloride is acetonitrile. And more importantly, it's refluxed, basically boiling. Now to make sure both carboxylic acid groups are converted, we should add 2 moles, or just excess thionyl chloride. So we form this compound, our acyl chloride. So as far as modifying alpha-Kg, we're done. This is ready for nucleophilic attack. So let's move on to forming the Gilman reagent, where we're using acetaldehyde. The goal is to form an alkyl halide via an alcohol. Let's say an alkyl bromide. And this alkyl bromide is then the substrate for the synthesis of a Gilman. So let's first form this. We start with acetaldehyde and we carry out any sort of reduction. Let's use sodium borohydride in ethanol water. And then we can take ethanol, and to form the alkyl bromide, bromoethane, let's use PBr3 in pyridine toluene. Now with our alkyl bromide, we can start the synthesis of a Gilman reagent. So to do that, we need to first form alkyl lithiums. And to do that, simply we just add lithium in a polar aprotic solvent. So let's call our alkyl lithium compound 3. We can take 2 alkyl lithiums and then synthesize our Gilman reagent. And to do that, we use cuprous iodide, again in THF, or any ether, and we form the Gilman. Now it can be written in a few different ways. The way I like to write it is like so, because it just helps me visualize what the alkyl group will look like. It can also be written like this, in a more abbreviated way, with a subscript 2, or we can also write it in its most condensed form, with ethyl in parentheses. This is all communicating the same thing. And now we're set. We have our nucleophile, and we have our electrophile. So let's mix compound 2 and our Gilman reagent, let's call it compound 4, and carry out that reaction, see what we get. So let's bring in compound 2, and to carry out our Gilman attack on both sides of our acyl halide, let's use 2 moles of Gilman reagent. Again, we can stick with a polar aprotic solvent like THF, and typically the reaction occurs at very low temperature. So the result of this is a diethylated compound. So let's first start out by drawing the backbone that we had with alpha-Kg. And remember, at carbon 2 we had our carbonyl, which was protected, and at carbons 1 and 5 we had our acyl chlorides, which are now converted into carbonyls. And we can number these carbons just like we can on our Gilman. Now 2 steps remain. We need to get rid of the protecting group and form alcohols out of these 2 ketones, which is exactly why we protected our alpha keto group to begin with. So let's take this compound, and we'll call it compound 5, and reduce the carbonyls with H2PT to C. We could use sodium borohydride, we could also use lithium aluminum hydride. This also works. And to carry out a deprotection of the acetal and come back to the ketone form, we just hydrolyze it with dilute acid and a little heat, which forms our product. One thing to note about H2PT to C. This hydrogen is in gas phase, and it isn't necessarily easy to control the molar equivalence in gas phase. So it would be correct to write 2, but it's okay just to indicate H2 gas phase, which would easily just reduce any carbon-carbon double bond or ketones.